Hello everybody, it's Brian. We're going to go over this. In this lecture we're going over the fundamental theorem of calculus. And so it's called the fundamental theorem of calculus because it essentially ties together the ideas of the derivative and the integral in like one kind of concise way. So to motivate this, we're going to go through a couple examples first to think about the ideas, and then we'll see. So here we have an example. We have this function f. Its graph is shown below. Okay, so you can see this. So the blue line here is the graph of the function f. So this is the part of the blue line there. All right, so g of x is the integral from 0 to x of f of t. And so we want to estimate, so g of 0 is the integral from 0 to 0 of f of t dt. Now, of course, you know the integral from the definite integral from a starting value to the same ending value is always going to be 0, right? G of 1 is the integral from 0 to 1 of f of t dt. Okay, so this is, it's g of 1 is the area that's, if I was to shade this in blue, that's the area here. Now this is a triangle with a base of 1 and a height of 2, so it's actually, you can see, this has an area of 1, right? G of 2, this is the integral from 0 to 2 of f of t. And so we're going to add to that one area, we have the second triangle, which I'll put in all in red. You can see that we're adding another 1, so it's going to be 1 plus the 2, so that's 3. G of 3, this is the integral from 0 to 3 of f of t dt. Now this is I have to kind of estimate this a little bit because I don't know for sure, but it's going to be 3 plus, I'm going to put in yellow, this area here. This is a little bit more than 1. I'm going to say 2/3 just to kind of give it something because it looks a little bit like a parabola, so I'm going to say 2/3. So I'm gonna let's say 2/3. So that's fine. 3 and 2/3. I'll leave it as that. G of 4. This is the integral from 0 to 4 of f of t dt. So this is 3 plus 2/3 minus an area that's underneath. I'm going to put this in green now. Now this is underneath. Now this is roughly, this is a little bit parabolic looking, and it looks like it's about the same amount that was just added. And I'm going to subtract away that 2/3 and give us a 3. And then finally, g of 5, the integral from 0 to 5 of f of t dt. It looks like I'm going to have 3 minus a 2/3. So as I said, this is roughly 3.67, and this is going to be roughly 2.33. So if we were to graph this out, we're going to graph this out. Let's put line here. So at 0, 1, 2, 3, 4, 5. Okay, we're not going to go up to 6. I'm going to graph out the points of y equals g of x. So we have g of 0 is 0, g of 1 is 1, g of 2 is 3, and then we're at 3 and 2/3. And at 4 we're down at 3 again, and at 5 we're at 2 and 1/3, roughly about there. So this is my kind of estimate. It looks like this is it looks like yeah, it's going to be kind of like this. That's about what I would say for g of x. Okay, so let's see where these ideas take us. We're going to we have this function g of x. It's the integral from a to x of f of t dt. Now a is 1 and f of t is t squared. So let's actually write this as the integral from 1 to x of t squared dt. Now this is a definite integral we can actually calculate, right? So we know that this is going to be t to the third over 3 and going from 1 to x. So this is going to be x to the third over 3 minus 1 to the third over 3. This is g of x, right? G of x is x to the third over 3 minus a third. Now what is g prime of x? G prime of x, if we take the derivative of this with respect to x, well, what other variable is there? It's going to be 3x squared over 3 minus 0. The derivative of a third is 0. So this is going to be x squared. So notice what this is. This here is actually just f of x. The f function is f of t was t squared. So f of x would be x squared. And this is essentially getting at the fundamental theorem of calculus. The fundamental theorem of calculus says if you have a function f that's continuous on the interval from a to b, and you define this function g as the definite integral from some constant a to x, which is a variable somewhere between a and b, of f of t dt, this is the antiderivative of f. In other words, g prime of x is equal to f of x. And so you can simplify this in kind of Leibniz notation, where we're saying that if we are taking the integral, remember that the lower bound, this is going to be constant. And this is constant where we're going up to a variable, upper bound. And then we take the derivative with respect to that upper bound, we're going to get f of x. This is the fundamental theorem of calculus, this idea that ties together both of these things. Now, it may seem weird that we would even have this, but there are a lot of good applications for the fundamental theorem of calculus. So we'll go through some more examples to kind of get this idea in mind. I mean, I know that in statistics this comes up a bunch, this idea of the fundamental theorem of calculus, especially with probability, with the probability functions, cumulative distribution functions, and mass functions. So this is very important for statistics and probability, and I imagine also for engineering and physics and stuff. But I'm not a physics guy, although I like it. I don't know tremendous amount about it. Okay, so here we go. Let's take the derivative of g of x, and so g of x is this integral. So let's, using the fundamental theorem of calculus, we'll do it both ways. The first way, I think that the problem here is like this is not something like actually performing this definite integral is going to be tricky, but we don't actually have the tools at the moment to do that. But the fundamental theorem of calculus says that g prime of x is going to be, so this here is, this is f of t is square root of 1 plus t squared. It's going to be f of x, which is just f function with an x put in place of the t. So it's going to be 1 plus x squared. That's what the fundamental theorem of calculus tells us. We don't actually have to find this integral. We don't have to find the antiderivative because we're taking the derivative of the antiderivative, right? Now, the lower bound, because it's constant, when we take the derivative, whatever that came out to be is gone because of, well, the derivative of a constant is 0. Take another example. So here we have, here up top we have x to the fourth as the upper bound. So what I'm going to do is I'm going to do a little substitution. This is something that you'll be learning about a little bit more in the next section, but I'm going to let u be x to the fourth. And I'm going to find u. This substitution is going to give me some other little bits. Now I'm going to, the derivative du is going to be, well, I'll say du dx, right? What's the derivative of u with respect to x? That's going to be 4x to the third, right? That's this derivative of u. Now I can actually, write this as du. Oh, let's just, yeah. So with that in mind, I'm going to put this in. I'm going to do this replacement, and we'll see where is this going to come into play. So I'm going to write this as d over dx of the integral from 1 to to u, the secant of t dt. So the fundamental theorem of calculus says we're going to get the secant of u times du dx because of the chain rule. And what is this? Du dx is 4x to the third. So I'm going to put that actually. So we have this is secant of x to the fourth times 4x to the third. That's going to be the derivative here. So this is another way of. So here we have another form of the fundamental theorem of calculus. And so this actually has two parts to it. The first we've already looked at. G of x is, if you have g of x is the definite integral from a to x of f of t dt, then g prime of x is f of x. That's the first part of the fundamental theorem of calculus. And the other side of things is just telling you that it's just giving you the kind of another way of saying how you evaluate a definite integral. The definite integral from a to b of f of x dx is big F of b minus big F of a, where f is any antiderivative of f. So this is something we were doing in the last lecture. So this isn't totally new, but this is a part of the fundamental theorem of calculus, which I'm not going to go through the proof of it in this video, in a future video perhaps. So, okay, so then we have this idea of the average value of a function. It turns out that because the definite integral gives you the area under the curve, if you divide that by the length of the interval, what that's going to give you is the average value of the function over the course of that interval. So this is how you calculate the average value of a function over an interval from b to a, or from a to b. Let's take a look at an example here. The average value of 1 plus x squared on the interval from -1 to 2. So this is going to be 1 over 2 minus 1. So that's going to be b minus a. That's 2 minus 1. And then it's going to be the integral from a, which is -1, up to 2, of 1 plus x squared dx. Now we can evaluate all this. So this is 1/3 times, what's this integral going to be? It's going to be x plus x to the third over 3 from -1 up to 2. Evaluating it now, and so this is going to be 1/3 times, let's see, I'll do the first part, which is going to be 2 plus 2 cubed, which is 8 over 3, minus -1 plus -1 to the third over 3, right? This is 1/3 times, let's see, 2 plus 8/3. 2 is going to be 6/3. So 6 plus 8, that's going to be 14 over 3. Then this is this here is, that's negative 1 minus a third. That's going to be minus 4/3. So it's going to be plus 4/3, plus 4/3. This is going to be 18 over 3 times 3 is 9. That's actually going to be 2. The average value of this function over the interval from negative 1 to 2, the average value. Okay, so we looked at a mean value theorem for derivatives. The mean value theorem for integrals tells you that that as long as your function is continuous, you can find a point on an interval where the function value there is equal to the average value of the function over that interval. Remember, for derivatives, it was if you have a continuous differentiable function, then you're going to find for sure that there is some point along this curve where the slope of the tangent or the derivative is equal to the average rate of change. Okay, so this is for the average value of the function. There's going to be some point from, so let's say the idea is that like you have some, if you have some interval here from A to B, okay, if you're able to calculate the average amount, let's actually move this over. Okay, so here we have these bounds, right? We've got the integral from A to B. So this here, the area in here, this is the average, or this is the integral, right? Is the area in green. So the average value is this area divided like times 1 over b minus a. So if we were to copy this thing over, the idea here is that we're able to find some point. I'm going to do a little bit of estimating about here. This is like roughly where C is. So if we were to cut this off and to take this area here, if we were to fill it in, we would roughly be able to, oops. So the idea is that there's like some point where we could cut this off at the top, take all of this, fill it into this valley, and you're able to get this rectangle where this height here, this is f of c, that's the height of this rectangle. That's the same as the average value of the function over this interval. Because if you have a rectangle, the area here, f of c times b minus a, and the area of that, all right, is equal to the integral from a to b, f of x dx. This is the height, this is b minus a. So the base times the height of this rectangle equals the integral. And you can see dividing both sides of this equation by b minus a gives you f of c equals 1 over b minus a. That's the average value of the function. Take this example here. If we have a function f of x equals 1 plus x squared, that should be lowercase, but such is life. Okay, so now the fundamental. So take this example of this function 1 plus x squared. It's a continuous function on the interval from -1 to 2, right? We've already looked at this in the previous example. The mean value theorem for integrals says there needs to be some value c on the interval from -1 to 2 such that the integral from -1 to 2 of 1 plus x squared is equal to that function value. So let's try to figure this out. Okay. So So first of all, what was this? We actually found the average value. We actually found 1 over 3 integral from -1 to 2 1 plus x squared dx came out to be 2, right? Well, is there some value between -1 and 2 such that f of c equals 2? Well, let's see. 1 plus x squared equals 2. That means x squared is equal to 1. X could be either, well, it could be plus or minus 1, right? Well, each of those is in the interval, actually. So c could be 1, or c could be -1. Either of those actually are on the interval. It's a closed interval, so it contains both points. So it turns out then that if you were to graph this thing out, so 1 plus x squared is going to look like this roughly, and it keeps going. Okay, so what we're seeing here is that if the area up in this area here is the same that would be in this little dip over here. So anyhow, so we found it turns out that either of those 2 points at either -1 or 1, the function value is equal to 2, and that's the same as the area, or the average area, because the total area is going to be 6 under the curve, 6 over an interval of length 3. The average value is 2. Well, that's it for the fundamental theorem of calculus as far as this lesson goes. Now it's just time to do some practice with this stuff. All right, bye.